So in the last lecture, I described the technique to perform a Hamiltonian evaluation. Basically, it amounts to exponentiating the Hamiltonian in an efficient manner. And there are various ingredients which I went through. I will give a quick summary of that. The problem was to calculate a matrix vector product, some initial state and some evolution matrix, and this had to be done in a n-dimensional Hilbert space. Okay. So we went through various steps of first decompose the Hamiltonian into block diagonal structure and then take appropriate products, exponentials, series expansions, find the good bounds for all the truncations or errors that arise in the process, and get some criteria for efficiency of the algorithm. And the final result for the complexity for the best algorithm which I described was order M, P, R, and C. There were the four numbers inside this algorithm, where M is a number of time steps, which in the optimal situation was just order t, and individual time steps were of magnitude 1 in appropriate scale. The scale was that the Hamiltonian was also bounded with eigenvalues which are of the order of 1. The P was order of power series. It was truncated, and that came from giving a bound on the Bessel function, and the result was log of, or this t is the same. As the evolution time. In the expression which I wrote down last time, I had forgotten this division. So the log term is actually in the denominator and not in the numerator. The R was a number of repetitions to suppress the error from whatever the success rate, the algorithm, it's in some sense a yes or no condition when you bring it down all the way to the qubit construction. And then what it does is takes this epsilon to epsilon to the power r over 2, which is needed because you want to suppress the error to an arbitrary small value in this bounded error probabilistic algorithms. And C is a matrix vector multiplication product. How much does that cost? And that goes from order D and B cube, this is classical, to the quantum case, where essentially the advantage from capital N to small n comes from superposition. You have to figure out how to use the superposition for every Hamiltonian individually because they all require different kind of structures. And yeah, this D which came here, the precision of the register, and it's again scaled like log of T by epsilon. And this is this is doing a it was actually log of m over epsilon in the expression which I wrote earlier, but since time step I have taken to be order 1, it can be written as that as well. And this is just to say that when you do a discrete calculation, even on our traditional machines, we run with some precision, say 32-bit precision register. The answer is not accurate enough, you increase it to 64-bit precision till you get desired accuracy. So these are all the parameters which went in, and the final result, you put all these factors together, and essentially this is order T. The subleading dependence on T comes from this factor of P. R and C are both related to how much precision you want and how much superposition you can do. Okay, so now I want to make some comments about what happens when you run it in practice, and also whether there are any related situations where the same machinery can be applied. Okay, so in practice, all these estimates or whatever you call they all were proved using some or the other kind of inequalities. Okay, and inequalities are not tight. What does it mean? That you in practice you can actually do much better than that. Why that happens? Well, because we use most of the time this triangle inequality adding up various terms, and they just added up modulus of everything. But in practice, there can be cancellations between different terms when you expand it in a series. And these cancellations are, in some sense, quite common in the kind of algorithms which I described, for the simple reason that all the expansion were done in an orthogonal basis. So whenever you do that, the orthogonality means that the successive terms, and they have to have zero dot product. Some of them is positive, there will be some other negative, and they will kind of cancel out. So if you do all the sum with just taking all the positive parts and ignoring all the cancellation, of course you will get a rigorous bound, but that is not tight. Okay. So that kind of routinely happens when you try to implement this in a computer, and we check that thing out. So there are cancellations among the terms bounded by whatever this is, say triangle inequality. This is just one of the reasons. The reason is generic, as I say, this is orthogonal. It's generic, but there can be other reasons also why these kind of things happen. So we tried running this algorithm for just simplest of the problems, harmonic oscillator. Nothing complicated than that. We knew all the answers, but just try to see where you put the Hamiltonian equal to the harmonic oscillator, how well this thing works in practice. And all these scaling behaviors came out, but you also saw this particular thing, that the errors don't grow as fast as what is given by this particular bound. They go much slowly. That means this epsilon is better than whatever these numbers are predicting, which is valid good. It's fine, but you also could see that for the harmonic oscillator where we just simulated for, say, one period, that is a usual thing. After that, there is nothing more in terms of the cyclic process. And then the 32-bit precision was not enough. We had to go to 64-bit precision coming from features like this. So, because we say that epsilon is machine precision like 10 raised to minus 9 or something like that in our classical computers. Log of that number is quite big, and this t has to be, well, we put 2 pi or whatever, simulate, etc. It went more than 30. And then the register could not hold it. We had to go to the next level available. So all those things can be tested, and they are simple programs or run on basically on PCs and basically verified all these kind of situations, that just how good is the convergence, how good is the control of the errors, etc. Of course, when you go to a classical version, things are well understood and we don't have to worry about the hardware. When you really try to do that in a quantum computer, all kind of other troubles will come with the hardware, and that you have to deal with in a different manner. So this is one feature. The other feature which could be done by essentially the same logic, but slightly different problem, which is exponentiating a matrix, but without the I in the exponent. I is square root of minus 1. Here everything was unitary. Suppose we want to just calculate a quantity like this. Which is common in statistical physics problems. exponential of the Hamiltonian with some negative prefactor. And the machinery goes through for all this criteria. You can break it up into different block diagonal parts, exponentiated, power series, expansion, etc. But one thing changes, and that is this algorithm works with the only change which happens in the power series expansion method, that there were Bessel functions which were appearing in the Chebyshev polynomial expansion, and they change from real argument to imaginary argument. So there are Bessel functions of a trigonometric type, and these are Bessel function of the exponential type. But the power series expansions actually have the same behavior, so the error analysis can be managed even when you replace Jn by In in a similar manner. Some small details change, but this error bounds are similar. How this can help? Well, there are different scenario. One particular thing which I can mention is that suppose I apply this operator to again some quantum state. It is not a unitary operator, but you can still do the power series expansion in a similar manner. You don't need a unitary operator for that, and the errors can be kept under control. What it does is, if I write it in a eigenbasis of the Hamiltonian, which is always something available for a Hermitian operator, there will be an orthogonal eigenbasis. Okay. So then it will look like e raised to minus of the lambda I times t, and i's are the set of eigenvectors. And this then can be rewritten as I'm not doing a projection operator, I'm just operating on a state vector side. Oh, that overlap, yes. That is some constant. Okay. So this term will be dominated by the ground state of the system because it has the smallest eigenvalue. So you can rewrite it as e raised to minus lambda 0 times t, and this in can be kept. And now you can ask what happens to the other terms. So the other terms will be larger than the ground state energy by various amounts depending on the spectrum of the Hamiltonian. So there will be correction to this, but there are related to this here, e raised to minus t times delta, where this delta is a so-called spectral gap. So what such a result will achieve is you can start with some arbitrary state, and if you apply this particular operator, the result, it will not be normalized because what these overlap factors are you don't know, but it will converge towards the ground state. And the rate of convergence is dictated by the spectral gap. So you can start with just some arbitrary state, and it is like converging towards its ground state projection. And this is a very useful technique which is used both in the statistical physics case as well as in a quantum system, that you don't know the ground state, you want to find an estimate for it, well, just apply this factor, and the overlap with the ground state will increase depending on how much this relative separation is. And it has been used not in the just in the quantum context, but in a lot of other places, in the classical simulation also. Only trouble was how do you generate this operator efficiently? Well, here you can do a better job. But it's a well-known technique to get an estimate of the ground state. It can be also put as some kind of a variational algorithm to get a bound, because all the terms, whatever these factors are, they're all positive. So you will slowly converge toward the ground state, but it will be from above, always. Yeah. This is an operator. It's the same kind of structure as what this thing is. It's not unitary. But I'm just saying that all this machinery works for non-unitary operators also.
So what is I on the right side?
The set of eigenstates of the Hamiltonian.
More right motion. More right. Yes.
Yeah.
Zero. That has to be ground state. Ground state.
Oh. No, this should be called the ground state, yes. Summation over? There will be all kind of sums suppressed by this term. You can have, it's not just one term. You can write an infinite series if you want. Yeah. All eigenvalues, whatever it is. I wrote this thing in plural. Okay, so it will be suppressed at least by this much. The higher terms will be even suppressed more, because you have higher excited state, the suppression factor will be the difference from the ground state eigenvalue, and it can be suppressed faster than this. That is okay. So something which you want to go to zero, and there will be some rate of convergence. The spectral gap actually dictates the rate of convergence towards the ground state projection. That's the point. Yeah. There is yet another thing which I can mention, which is more general and which is still an open problem about how to tackle it in a most efficient manner, but something can be said about it, and that is related to this, but calculation of thermal expectation values. So thermal states are not even states in the Hilbert space. You have to describe them by density matrix. Okay. And that definition is the density matrix is given by e raised to minus beta h, and this z is called the partition function. It is a normalization condition which was not written explicitly in this particular case. But the structure is similar, that you have a negative exponent of the Hamiltonian. Beta is related to the temperature, inverse temperature. So 1 over beta is. So the question is, this is a mixed state. Okay. Can you prepare this thing efficiently? That is the question. Of course, if you want to deal with a large space, whatever is a dimension of the Hamiltonian, this expression is standard and it's exact, but you don't want to do that much work. That is essentially the point. So that determination you can't do completely if you want to calculate the density matrix, because the density matrix has whatever n by n structure, and if you want to determine everything, there is no shortcut. But you can ask that I don't want to calculate the full density matrix, but I only want to calculate some expectation values. So that is what you are going to ultimately compare it. So suppose you want expectation value of some operator. So the definition is just this. If this operator is again some n by n matrix, there are no shortcuts. You have to do all the hard work. But the operator can be constrained to have some nice structure. Okay. And the typical thing which we use is this O is something which is local. This is to be taken in the tensor products sense, that the system is made up of many parts and the O is going to be focused on a few parts, not on the other stuff. And when you have such a structure, what you end up calculating is some operator at this local points and identity on all the rest. And that becomes a reduced density matrix. When you have identity on all the other stuff, that part of rho just is summed over and you have a smaller problem. And that can be a situation where efficient calculation is possible. Okay, so rho is and how does this localization occur? Many problems you calculate what are called some n-point correlation functions, where operators are fixed at certain points. You calculate the product of whatever non-trivial objects sitting at those endpoints are. You trace over everything else, which is the reduced density matrix. And as long as those number of points is limited, the dimensionality of the reduced density matrix will just depend on the number of points. The rest of the stuff is all gone. So then you can ask that, yes, I have this density matrix, but I'm going to trace over all of the other stuff, and can I use an expansion of this particular sort? The answer is yes, you can do it. So O can be expanded in its eigenbasis. That is our choice about what correlations you want to calculate. The only thing in quantum mechanics is that all the observables, there will be Hermitian objects, and you know what the eigenbasis of those, whatever you want to measure it is. If it is say a Pauli matrix, you are measuring the spin, you know what the eigenvalues of up and down is, so you can be always return that these are all sum over the eigenbasis with the corresponding eigenvalues.
When rho is replaced by the reduced density matrix, operator O also is replaced by the tensor product of the points where it's not identical. Or
yeah.
So both are to be replaced.
Yeah, so rho may not have the what you call factorized structure. It can be a complicated matrix, and this will be the case when there are correlations. But because the O has gotten factorized, you will get a trace of rho in the larger space, which is the definition of the reduced density matrix. For calculating the reduced density matrix, rho does not have to be factorized. You can calculate it for any density matrix. You can choose a basis, that is fine, but you don't have to necessarily factorize it. So the same kind of thing that O is equal to some eigenvalues and some vectors, and once you have that structure, you can use this kind of algebra to evaluate term by term. Okay. Here, there is no shortcut. Whatever the number of eigenvectors are there, you have to sum over all of them. But the point is that you are choosing the operator to in a simple form, and so the number of eigenvectors will be few. Just calculate them one by one, and then you will be able to calculate this expectation value as well. A more general problem actually about how to prepare this state itself is open, in the sense that people have tried various kind of tricks, but nobody has found a efficient algorithm to do it, and this state is called the Gibbs state. So this is called the Gibbs state preparation problem is open in terms of finding an efficient algorithm. It's an important problem for many different contexts. The most important one is that if you take a system and put it in thermal bath, it will go to that state. The question is now, it happens in real world, how well your algorithm is going to do the same job. Okay, and that is something which is not completely done. People have made improvements here and there on certain parts, but yeah, general situation is unsolved. So, okay, this is all about various kind of applications about exponentiating the Hamiltonian and what can be the applications for it. Now I want to go to the last part of the simulation problem, which is measurement. We did all the evaluation and obtained the final state. Now, if the job is to read all the components of the system one by one, that is hopeless because it's an n-dimensional Hilbert space. And just reading it or writing it or copying it, whatever it is, it will be order and effort. Forget about calculating anything with that. So for a general operator which just tries to read all the terms one by one, you are not going to get any advantage. It's a hopeless task. But now you can ask again a question, can I calculate some properties of this state efficiently? I don't want everything, but some properties, and the typical properties in all the statistical mechanics or quantum mechanics have some expectation values. And that question again can be answered under certain assumptions that yes, you can design an algorithm, so efficient calculation possible, something very similar to what went up over there for what I'm going to call k-local operators, which means that O is whatever the operator you choose, it's concentrated at k points and equals identity elsewhere. If I have such a situation can construct an algorithm which will do this expectation value calculation with all the kind of bounds on error probabilities, etc., etc. And my next job is to describe how it can be done. Okay. So for that choice you want to make, I will take the simplest case that the system is decomposed into a bunch of qubits, whatever it is. So whatever this n is, it is 2 raised to the small n. Okay, so take system of n qubits, then expand any operator in Pauli basis, which can always be done because whatever this operator, it's going to be Hermitian, and for a system of qubits, all the operators which you can write are some set of Pauli matrices, nothing more than that. And so you can write O as summation over OI, which can be written as a I have to be careful with the indices. It's a tensor product. I is not a good enough description. Well, let me break it up into two parts. Some decomposition where each OI is some sigma mu 1 at 0.1 all the way till sigma mu n at point n, where n is a number of qubits. So some decomposition. And this is a sigma matrices are a complete basis, so this can always be done. Yeah, so sigma mu is the 4 Pauli matrices, including identity. Yeah. Yeah. So k points means that most of the n minus k places will have an identity matrix, and those k points will have one of these three. Okay. So I can write it explicitly. K local operators have 3 raised to k non-trivial terms. All the other stuff is identity, which you will do the calculation, it will go back to calculating a reduced density matrix. And if k is some finite number, 3 raised to k will be large, but it will still be some finite number, whatever it is. Okay. So this Pauli basis has several advantages. One of this is a Hermitian, so it allows such an expansion for any arbitrary operator. The second thing, it's also unitary. So you can treat it like an evolution operator also if you want. And third thing is the eigenvalues are all known plus and minus 1. They are maximally distinct. So whatever this Pauli basis element, and all these things help quite a lot. So Hermitian, unitary, and plus minus 1 eigenvalue. Simplifies the job of the calculation quite a lot in terms of finding the expectation values and also summing over the possibilities of different answers when you perform some measurement. The eigenvalues you will get in measurement are always plus 1 and minus 1, nothing else is going to appear. When you take this full summation, there will be a Pauli matrix at all the n locations. But n minus k location, that matrix will be identity. The other k locations, it will be one of those 3. And that is this number 3 to the power k. 3 possibilities at k different locations. Okay. So now we have to worry about measurements going to be probabilistic. Huh? I goes over all full decomposition. If you want it, it will have 4 to the n possibilities because each one of them has 4 possibility and n possible indices. But lots of those terms will have 0 coefficient, which we don't worry about.
Each OI should have each OI should be k-local or the whole O should be k-local?
The whole operator has to be k-local. OI is just a basis of expansion. That means lot of these coefficients beta I are going to be 0.
So each of the OI, there are only k, each OI has only k different positions.
Yeah.
Which can take different Pauli operators.
Yeah.
At those same positions.
Yeah. So those are the terms which will have non-zero expansion coefficients. The other ones are all zeros. That is the assumption. So now the job is that measurements are going to be probabilistic. That means sometimes you will get plus 1 and sometimes you will get minus 1, and then you will determine the expectation value of some kind of average, but you want to find out what is the error on that average. Because one trial you make, you will just get one eigenvalue, nothing more than that. You have to make multiple measurements, take an average, and then you want to determine how accurate is that particular average. So that is the game. There will be some criteria we will define that I want to calculate this expectation value with error epsilon. So this error on O has to be found in terms of number of measurements and the challenge is to optimize this so that whatever the number of measurement will become our computational complexity in certain sense. It should have log of epsilon sitting inside it, not power of epsilon. That is the target. So, well, now can slowly proceed in that particular direction. There are various simple ingredients which I can quantify, but yeah, one of these things is, what is the rather the simplest part which follows from this is a again some kind of triangle inequality, nothing more complicated than that. And this is 1. Eigenvalues are plus or minus 1. You don't worry too much about it. So it just gives a bound on this quantity, how many quotient are non-zero, and you add them up. And we'll say that what is the right word? Just and this object I can kind of define as some sort of norm of the operator. Okay, it's a linear norm, but you can take it to be a definition, doesn't matter too much. So what we essentially need is if this sigma I, that is this what I wrote here. This particular expression if I make some measurement of some Pauli operator of this type to some accuracy epsilon, okay, and then I can say that this object is less than or equal to epsilon times the norm of O, whatever I defined in this particular can, because I had this term here, but I am putting an error on each of these to be epsilon, and that is a target that whatever Pauli operators you want to measure, you want them to measure to this criterion epsilon, and the error then will follow. It is not any different, it's bounded by the same quantity, and you don't have to worry too much about calculating the error on the operator, provided you calculate the error properly on each of these Pauli terms. It's just a simple linear relation, and one of them is equivalent to other. So now the job is to calculate this. That means I have a circuit in which I will measure this operator. And important point is that this OI should be measured collectively and not by measuring individual factors. What do I mean by that? This is the operator I want to measure. I'm not going to measure sigma 1, sigma 2, sigma 3, all the sigma individually and multiply them together. In principle, I can do that, but that is not a good way to do the job, because I only want the final value, which can have many permutations and plus or minus 1. The product will have the same result. Yeah. This is a linear norm in terms of the eigenvalues. There's a quadratic norm also which is used, but in general they are all having similar bounds. So I'm just not worrying about that kind of details. You can use any norm which you want. This is actually, I think it's called a linear norm, not the quadratic norm. Okay, so how do I measure a collective observable without measuring the individual parts? And that can be done by controlled operations in quantum circuits. And for simplicity, the best thing is just to give an example, and I will just take a two system. So e.g. Measure say sigma 1 on the first qubit and sigma 3 on the second qubit. Suppose I want to do that, there will be some state, 2 qubit state psi, and I have to get this is a ancilla, and ancilla will be measured at the end, and you can call it 0 and 1, or you can call it 1 and minus 1. They are interchangeable in any measurement. In qubit system, you will write 0 and 1, but we will convert it to 1 and minus 1 when substituting inside here. So Now what you need, this part is easy. You want to measure sigma 3 of this second qubit. It has the 0, 1 basis. The 0 state will correspond to, well, eigenvalue up, the other one corresponds to eigenvalue down, and then you can easily include that by a control knot operation. Okay, you can put this ancilla initial part as a state 0. So if you want to measure sigma 3, the upper component, nothing happens, it will remain 0. If you want to measure the lower component, it will flip. And just for the variety, I didn't write sigma 3 on this one also. It becomes too easy. You have to put 2 control knot. But put sigma 1, and that is not too complicated. I will do sigma 3 only, but after changing to the Hadamard basis. Okay. So this will give the corresponding eigenvalue of this. It will show up as 0 and 1 in qubit notation, but I can call them +1 and -1 by expectation value notation. And then I ask, what is the output over here? It will make the whole thing completely explicit. These are control operation. This was a 2 qubit, there was a third one. So everything is going to get untangled. Okay. And then I can write the 2 states in a 3 qubit untangled notation, which they are basically projections. So it is identity plus eigenvalue for sigma 1 on 1, sigma 3 on 2, identity 0. This is a projection operator for eigenvalue equal to +1. And the other possibility is the minus. So now if I measure it, I will be measuring this last bit, which is the ancilla. It will give me the eigenvalues, and the initial state gets projected onto its corresponding component. These are the usual rules of quantum measurement, which I am following, but the point is that you can always do it for any of this Pauli basis operator in a rather simple quantum logic. And the important point is you are not measuring the individual states. If you do that, actually the effort required goes up exponentially. Here you are summing over all kind of +1, -1 combinations in the whole product, which can be of the order of 2 raised to n or whatever it is, something of that type. So this is a efficient way of calculating this collective value of whatever the contribution to this expectation value of OI is. And yeah, so now we did the first step that I want to calculate it. I can do this job to find how often it is 0 and how often it's 1. And then the expectation value is counting the frequencies. How often is 0, otherwise 1, add up it together. The point is that I want to get it accurate up to some error epsilon. Okay. So I have to, well, introduce a notation for that as well. So let P be probability of getting 0, then the expectation value is 2p minus 1. Well, I wrote it quickly, but I can do this. P corresponds to plus 1, 1 minus V corresponds to minus 1, added together, and that is 2p minus 1. So you can forget about counting two numbers, you have to just count one number p, because that's a binary case, nothing more than that. Okay. And now the job is how many measurements you need to get an accurate estimate of p. Okay. And for that now we have to do exercise in probability theory. The standard technique in computer science of developing bounds on various quantity, but I will go through it in a straightforward manner, and algorithm to get this accuracy sufficiently well is known as the Chernoff bound. And the technique, whatever is called as a Chernoff bound, is to estimate p so that the dependence on epsilon is logarithmic. Log of 1 over epsilon appear, not a power of epsilon. So this is a standard thing you can find in many textbooks, but I will describe it probably because most of you will not have heard about it at all. So let me proceed in steps. So let xi be a binary variable, which means that it can take two values, plus 1 and minus 1, and the average will be 1 over m times the sum of all the two, and what we assume in the probabilities distribution that this xi are described by this acronym which I have mentioned sometime before, independent, identically distributed random numbers. Okay. So we will assume this a quantum measurement has that property. First time you measure, you get something. Then you will run the whole algorithm again, identical algorithm, measure it again, it will give some eigenvalues, etc. And then you get a whole distribution of these results. They are the results of the measurement, but the point is that they have this particular property. And then with that property, now you can estimate. This is the mean. What is the error? The second moment. That is what you have to bring it within this epsilon. Then you can say that I have a reasonably accurate determination of the mean. Okay. So I have to put in some explicit criteria. So there are two different numbers, and this is just the mean, but I need a exact answer. So let exact how do you define the exact value? Well, you increase the sample size to infinity, and then the fluctuations will be ignored. So the point is to bound the difference between this value and something obtained with a finite number of m as a function of m, whatever it is, how fast it is going to converge. And so I need some parameters and some well-known. So this has to, the quantity which has to be bounded is probability of xi, this finite thing, minus mu greater than delta it can go either way. So that is, we want that when are you confident about this finite sample mean? When the probability that this difference is larger than some value delta is tiny. You want to push that thing to as small value as possible. And so now the question is to estimate this. That is the technique which leads to the Chernoff bound, and it can be done in two parts. One of them is this number is positive, the other one it is negative. The two tails of the two.
Greater than delta or less than delta?
You have to find an upper bound on this, which will be the analog of getting a wrong result.
So this is the failure probability. This is the failure probability.
Failure probability, yeah. that has to be related to epsilon, because epsilon everywhere is probability of getting something wrong. We want that to be sufficiently small. Okay, so now the analysis starts, which uses first thing what is known as a Markov's inequality. It's a simple thing, but it is very heavily used in many of this probability analysis. So for a variable which is always positive, okay, what is the what is called expectation value? So no, it's f is a distribution. So notation again. Yeah, f is actually the distribution inside it, and you are trying to, okay, so this is probability of x which is bigger than a is easier to write it in this integral form. You can write it as a sum also, no problem with this, that this is not x greater than a, but I have to fix this quantities, but the point is actually this object is bounded in a simple manner, because x is always positive, and in all this region x is greater than a. I just take it out and put the lower bound on it, and this is actually now the distribution from a to infinity. So this is equal to a times probability of x greater than a. That is what this is. This quantity is related to the mean. So I start with this. This is 0 to infinity x fx dx. Then it is bounded by the partial integral. Instead of going from 0 to infinity to some finite value, because x is always positive and f is a probability distribution of x, which is positive by definition. So this is the mean of the whole distribution, and this is a tail of that distribution. So you can get the probability of something being in the tail, which is what we want to use, in terms of the mean over the whole distribution. That is essentially the point. And the extra factor which comes is the boundary where you want to put the cutoff. How much is the range covered by the tail? And that is this variable A. Because I'm going to use X, here it will become delta. Okay. So now the Chernoff bound is a very simple application of this inequality, and it starts with this quantity, and writes it in a different manner. So I will just take one tail for the time being. So this xi minus mu greater than delta. But these distributions of xi are not of this type where xi is always positive. We know that it can take +1 and -1. So you get rid of this by a rather simple trick. You find a function which is monotonic and also positive, which is exponential. So you put the whole stuff in the exponent, that is s sum over I xi minus mu. I am removing the factor of m also. So I took care of this, and then e raised to m as delta. And here for all s. I just raise this whole stuff to the exponent. The exponent power is left free, or it will work for any value of s. And there was this 1 over m sitting in the definition of the average, that also I have put in the exponent. Okay, so this is basically just an equivalent statement. This is true, at the same time this will also be true. The point of doing this is, now this function, whatever this stuff is positive, the argument, and so I can apply Markov's inequality to it. Okay. And that gives the first step. Where you will put all the values inside it. So this is a Markov inequality, which will be, now the probability is gone, it will be expressed by this means. So the part which is not known is the mean of this quantity, the first term, and the rest of the stuff, whatever it is, it's some numbers, and you put in the values, and this will be m as mu this probability is the average, which is what is appearing over here, divided by the place where you cut off, and that produces this factor. MS mu comes from here, which is minus, taken to the other side of the equation. Yeah, so this factor was on the left hand side. I shifted it on the right hand side by flipping the sign.
And it's 1 by A.
Hmm?
Expectation by A.
Yeah,
So,
I want to calculate this. It is the expectation value divided by this, but the what is this thing here is a value at which is e raised to minus ms mu. 1 over that is e raised to ms mu.
I think it's minus. A is A e raised to ms mu plus delta.
1 by
You can change this on this side of the equation also. If I can write minus m mu and minus m delta by making this greater than 1. The greater than 1 is equivalent to greater than e raised to 0. It's the lower limit of this integral. The analog of A is actually this term, m e raised to minus m mu s. This stuff is the variable part. These are just some constants which you have to take care of. And let me just check whether I'm making the sign mistake or not. Maybe I am. Yeah, there is expectation value. I have to rewrite it in different manners. Okay, let me write one more step. To avoid confusion, so put everything on that side. Probability e raised to s xi greater than e raised to m s mu plus delta. Okay, that is more suitable for applying this value. So now I can write expectation value of e I xi oh, 1 over, yeah, that was a mistake. Okay, it is to minus ms. Okay, and then what is this quantity is e raised to s p plus or minus s times 1 minus p. Not in the exponent. making a lot of unnecessary mistakes, but yeah, that's what it is. And it is the same for each value of I because of this identical independent distribution.
Less than or equal.
So there are two things here. We could explicitly write it in terms of P and 1 minus P, which is what we want because it is related to the accuracy of the observable. And the other thing is that the quantities are very simple functions of this variable S. And that we can now take advantage of it, that you have this bound and S can be chosen to minimize the bound. Okay. Now let me just finish this and I can continue next time. So S is a variable parameter. I have the inequality and I want to make this thing as small as possible. Find the best value. So that function is kind of straightforward. Can erase some things, yes. This is just this whole thing raised to power m because I have to do it for every m. So can be rewritten. So this quantity e raised to s I xi is equal to p e raised to s plus 1 minus p e raised to minus s to the power m, and I will put another bound on it which is convenient. This is a let me do it in steps. I factor out this quantity completely. 1 minus or plus p times e raised to e raised to 2s simply minus times p. Okay. And that can be bounded by yet another trivial identity, which is exponent of m here also. So this is using the what you call another trivial identity that 1 plus z is less than e raised to z. Something like that. So whatever this stuff is, I put it that also in the exponent. The point of putting everything in the exponent is I want to take a log and get rid of all these things to get a simple result, because it was done artificially to make everything positive, but I want to finally remove everything. So then the question is now minimization. Which means I take this and this other part and differentiate with respect to s to equate the derivative to 0. Everything in the exponents, I can just differentiate the exponent to get the correct value of 0 as well. There is not much of a problem. And the answer is that e raised to 2s gets determined as 1 plus omega, where omega is delta divided by 2p. So I basically differentiated with respect to s, but in the exponent. And this gives -1, which is sitting over here. This term, derivative of it, it will give me mu plus delta, and that gets readjusted with this p. You have to write down this value of p, which is related to this mu in some sense, which is equal to 2p minus 1. That is the quantity, that's the definition of mu. Okay, so that's some amount of jugglery, but you can explicitly solve this result, and then the job is to find out what this bound actually tells me. So I will stop here, the time is already over, but I will continue with this exercise in the next lecture.